So I welcome you all to this first day of the HAFL Swiss Week. We are very grateful that so many people have joined today. And we will be talking about monitoring ecosystem services in Swiss cities, and we will be presenting practical experiences from Switzerland. And for today, we have invited four wonderful guests who will be presenting the work that they have been doing so far in this domain. First, Oliver Gardi will be talking about monitoring trees biomass outside forests. He has studied environmental science at ETH, at the Technical University in Zurich. And since then, he has been working on balancing the carbon storage services of forests and forestry in Russia, in the tropics, as well as in Switzerland. One focus of his work as a research associate at the Bern University of Applied Science is the analysis of remote sensing data. Additionally, he coordinates the study specialization climate change and sustainable land use. As a second referee, we have Michael Fuchs. He will be talking about monitoring ecosystem services in Swiss cities, a practical experience. He is a landscape and spatial planner and has worked in private offices as well as the University of Applied Science in Rapperswil. Since 2017, he has been working for Grünstadt Zurich and in open space planning with a focus on urban trees and urban climate. Since 2020, the technical planning head mitigation is available, and they are working on this in this domain to develop a technical planning urban trees. Exactly. Then we have a shared presentation from Andrea Salutz and Naomi Züricher. Both will be talking about quantifying ecosystem services of urban trees, the potential of iTree. Andrea Guillon completed an apprenticeship in a landscape gardener, followed by a bachelor degree in environmental engineering with a specialization in plant use and urban trees. He is working at ZHAW, at Applied School in the canton of Zurich in the research group for plant use as a research associate, and is mainly concerned with physiology of trees, the effect of plant carbon or urban trees and substrates, and climate change adapted urban trees assortments. Naomi Zurich, I assume that most of you know her. She works for ArboCityNet, that's her own firm. She is an urban forester, a consulting arborist, a trained beekeeper, a certified master composter, and an affiliate member of the iTree team. She has over 40 years of professional experience in this domain, also working with her own firm, ArboCityNet. She has she's currently retired and lives in Lucerne, and she is still working in this field and is trying to advance the philosophy, art, theory, and practice of urban forestry. These are our referees for today's morning, and I would like to recall the rules of today. So I will thank you if you could mute yourself. And if you want to pose a question, it will be great if you can put it on the chat. Vera Krill, who is my assistant today, she will be collecting the questions, and then I will give them, I will post them to the referees. My name is Jerylee Wilkes-Allemann. I'm currently working at the same institution of Oliver Gardi at the Bern University of Applied Science at the School of Agriculture, Forest and Food Science. So I am responsible for urban forestry in teaching. Good. Before we start, we have prepared a small surprise for you, which I would like to share now. We have been running a video, a paper ball video, asking one question to some experts all over the world. And that's about 3.5 minutes, and I would like to share that with you. And after that, we will start with the presentations. Okay, that was it. And we will share it on the webpage of the HAFL. And just for the program of today, we will have blocks of three presentations. And in between, we will have 5 minutes of a short break so that you can a little bit pick a coffee or just relax for 5 minutes. And at the end, we will have around 20 minutes of discussion. So I would like to give the word to Oliver Gardi and have fun with today's webinar.
Thank you, Jerylee, for the introduction, and also thank you, the organizing team, for inviting me to today's HAFL seminar to present our work that we have been doing in the past years on monitoring the biomass of urban trees, particularly, and more general, the biomass of trees outside forest. Can you see my screen? Great. So these are activities that we have been doing for about the last 5 years, together with the Federal Office for the Environment, the BAFU. And why the BAFU is interested in monitoring the biomass of urban trees. It's mainly about sequestration and emissions of greenhouse gases, CO2. You know that countries have to report annually on sinks and sources of greenhouse gases in the framework of the UNFCCC, Global Climate Policy. And in this annual reporting, countries also have to report how much carbon is stored in forests, how much carbon is stored in the soils, and also how much carbon is stored in trees outside forests, and how those terrestrial carbon stocks, how they evolve over time. So this part of the climate reporting, it is also known as the LULUCF sector, land use change, and forestry. Some of you probably have heard of that. And of course, one of the main carbon pools in this LULUCF sector, beside all the organic material in the soil, which is a separate story, but with regard to the biomass, of course, it's all the biomass that is stored in the trees in the forest. This is the major carbon stock. And this is well monitored in Switzerland since about the last 30, 40 years when we started with conducting national forest inventories. The first has been done in 1983 and 4. And now we last year, I think it was that the 4th national forest inventory was finished. So we have quite excellent, very good data about the state of our forests and also the carbon stored in the tree biomass in forests. But in contrast to that, we have very limited knowledge currently about the trees, the volume of trees, but also the biomass of trees that are located outside the forest boundary. And so it is an objective in this national greenhouse gas inventory to improve the methods, to improve the data from one year to the other. So there is an interest from the side of the BAFU to improve also the availability of data on trees outside forests, and in particular in this context, the biomass of those trees. And it's not nothing. There has been a study in 2011 from colleagues from the WSL, from the Swiss Research Institute, Forest Research Institute. By analyzing aerial images, they came up with a figure that 6% of the trees in Switzerland are actually located outside forest boundaries. And a large part of those trees outside forests are located in settlement areas, so contributing to what we call urban forests. And in major Swiss cities, the tree cover ranges about 16 to 22% of the area of the settlement area that is actually covered by crowns of trees. So this is a considerable number. But the area covered by trees in the settlements, Swiss-wide, it's actually decreasing. That is something that comes out from the Swiss aerial statistics. So we are losing actually trees, tree areas in the settlement. I think that Michael Fuchs, who will do this presentation following me, will present the case study on Zurich, where they looked at those figures in more detail. So with regard to the quantification of tree biomass in urban settlement areas, we did a case study in Bern a couple of years ago. The first challenge we had is actually to get to know how much biomass or how much carbon is actually stored in a single tree in an urban environment. We have such formulas and models available for estimating the volume of trees in forests, and the volume, you know, it is closely linked to the biomass. So when we know the volume and when we know the wood density, we also can calculate, multiply those figures to estimate the biomass. So we have those functions for our forests. They have been developed over the last decades in order to get a good idea of the timber volume in the forest. But how do we know whether those formulas also work for urban trees? Because urban trees are quite different from forest trees with regards to the shape. So that's the first thing we did, is we actually measured the biomass, the weight of trees that had to be felled for sanitary reasons. We measured the weight on a large scale. In this case here, it's a truck scale that you see in the figure on the bottom left. And then we took samples from the tree and we put them in the oven in order to measure the share of the weight that comes from the water ratio, water content, and with this then we really could determine the dry biomass of the tree. And this we did for 21 urban trees in Bern. We measured the weight, the dry weight, and then we compared it to the estimates that we get from different functions, biomass functions. So first one here, try to activate the laser pointer. So the first one here, these are these Swiss volume functions that we use in the National Forest Inventory, the ones that I just mentioned, that the functions we use to estimate the volumes of forest trees. And then we have here another model that we tested. It's actually the international recommended default model to use if no better data is available. So this is from what is this IPCC proposes to use in order to estimate the biomass and carbon stocks of urban trees. And then we have another function that has been published 2015 that is based mainly, that has been developed in tropical forests, but nevertheless we thought, why not, let's try it. And then we compared the estimates of those functions with the biomass that we actually measured. These are the black dots. So you see how close or how far the estimates of the different models are from the actually measured biomass of the trees. Here you see how the biomass usually increases more or less exponentially with increasing diameter at breast height. So the best model, the one which comes closest to what we measured, is actually the one that has been developed for tropical forests, and not the one we use in Switzerland for measuring the volume. And why? So here you see the formula. HEB, this is the acronym for above ground biomass. That is what we are interested in. And then you see here, this is the biomass. Actually, it's a function of the wood density. This is the rho here, the diameter at breast height squared. So this is somehow the basal area of the tree, and the height. So we have the more or less the volume of the trunk, diameter squared times height, multiplied with the wood density. And this gives us an estimate of the biomass, of course, with some coefficients that are applied to this function. So it's a generic function. It's not specific for a specific tree species. With the wood density here, we can really apply this function to any tree species. And what is particular on this function is that it takes also the height into consideration for estimating the biomass. And in forest functions, in volume functions that we use in forestry, usually we just take the diameter as a predictive variable, but not the height. And I think this is the reason why this function here actually performed best for urban trees, because it also considers the height of the tree. Okay, we have now identified a model that provides quite precise estimates of the biomass of individual trees. Next, what we did is that we inventoried all the trees that were located in 25 to 25 meters plots in 179 plots in Bern. So to get an idea how much biomass is stored, tree biomass is stored on this specific area. And the idea there was then to compare whether this biomass we found on the plots, whether this is somehow linked or correlates with the volume actually of the trees that we can see on laser point clouds. So these laser point clouds, it's called lidar data. It's provided by airplanes that fly over a surface, an area, and they scan the three-dimensional structure of the surface. And from these point clouds, we can separate what are buildings. For example, here, the red part, this is the building of the University of Bern, the main building. And we can separate what is ground. These are all the blue dots. And we can separate also what is vegetation. In this case here are the yellow dots that we can clearly recognize as crowns of trees. So what we were interested in, whether the biomass that we measured on the ground, whether this is somehow correlated with the volume, the number or the density of yellow points that we can find in this in this lidar data. So how we processed this lidar data, we have this point clouds here, that is what we see on the left hand side. And then we calculated first what is the crown cover, and this we did on 10 to 10 meter pixels. This is just the percentage of laser points that were classified as vegetation compared to that is what we consider as crown cover here. And then we also measured, or we assessed what is the average height of the points that were classified as vegetation. And by multiplying those two figures together, we get something like the green volume. So the density of vegetation points and the average height of this multiplied together. And this we compared then with the biomass of the trees that we measured on the plots. And we were really surprised that we found it quite a strong linear correlation between those two. So it means we are able to quantify the tree biomass based on the lidar data once we know this relationship. We then used this model in order to produce this biomass map for the settlement area of Bern. Yeah. These are then the average biomass stocks in above ground tree biomass in different land use classes in the settlement area of Bern. And you see overall we found something like 12 tons carbon per hectare stored in the above ground biomass of trees in Bern. And this is about, it's not nothing, it's a considerable number, 12 tons per hectare, but still we have to compare, when we compare it with the biomass actually that are stored in Swiss forests, it's about 8 times less. So in Swiss forests on average, we have about 100 tons of carbon stored in above ground biomass. In Bern, it is 12 tons carbon per hectare. Okay, it was then decided that this is an approach that we would like to scale up and not just use it for Bern, but use it for quantifying and monitoring biomass of trees outside forests for whole Switzerland. So the first thing then we did is actually we really proved again whether this biomass function that we used, this function that has been developed for tropical forests, whether this is really the appropriate one to use. And again, I come back to this point now that urban trees or trees outside forests in general, sometimes they have very particular shapes that are very different from the shapes of trees that we would find in forests. And this we have to take into account. So here, for example, you see these trees, they have, I think these are willow trees. They have diameters. We rarely find them in forests. It's more than 1 meter, maybe 1.5 meter in diameter, but the height is very limited. So something like 6-7 meters now. And this shape, we never find it in forests. And we looked at this and we compared, I hope you can see it on the slide. This is the height on the y-axis and the diameter on the x-axis. So it shows us the shape of the trees. And you see here actually the forest trees, these are the crosses. They are more or less on one line. So the ratio between height and diameter, it's a factor. It's more or less a number, a stable factor. So it means when we know the diameter in the forest, we have a pretty good idea about the height of the tree as well. For urban trees, you see here, it's a cloud of points. So there it's a huge variety and diversity of forms and shapes of trees in the urban area. And this we have to take into account when we want to have a model for estimating the biomass. The height is an important predictor as well. So we measured another 62 trees in Switzerland that had to be felled in 8 cities. And we, again, same method, we measured the weight and then determined the dry mass. So visually, we measured the height, the diameter of this tree. And in addition to that, what we also did is we tested whether we can get more precise estimates of tree parameters when using terrestrial laser scanning. So again, really measuring and assessing the three-dimensional structure of a tree. So here on the left-hand side, actually this is the same tree that you can see here. It is in Bern on the Grosse Schanze. You see this is the three-dimensional structure, the point cloud that you get from terrestrial laser scanning. And this data was then processed to really get the branches, the volume and of the trunk and the branches. And of course, when having this three-dimensional model of cylinders, we can really estimate directly the volume from this terrestrial laser scanning. And of course, this gives us a very precise idea about the biomass. And again, then once we did this field measurements, then the trees were felled and we measured and weighted the weight and the biomass. And so this is an article that has recently been published with the results of this data. And so on the x-axis, you see always what is the real biomass of the tree that we measured by measuring the weight of the tree. And on the y-axis, you see first here, this is the biomass estimate based on terrestrial laser scanning. And you see how nicely those points are really on one line. So with this TLS method, we can get a really precise estimate of the biomass. But also with the traditional methods, by measuring just the diameter and the height, you see that we get quite a good estimate of the tree biomass as well. Okay. It's the same function, finally, that we identified to perform best. The one that I already presented, is the function that has been developed for tropical forests. So again, the next step, we have now re-identified the best model for estimating tree biomass. Now we are collecting, we do inventory, tree inventory on selected reference plots. And the idea is, as we did it in Bern, that finally we use this data to calibrate, to find the correlation with the lidar, the green volume that comes from the lidar data, in order to then produce Swiss-wide biomass maps. That we are doing now. In Switzerland, we are very lucky that we have this lidar data available for the whole country. The first lidar mission from the Swiss Office for Topography, Swiss Topo, was done between 2000 and 2008. This lidar data was mainly used for constructing surface models, but is not really suitable for measuring tree volumes, because the point density is rather low, only 1 point per square meter, and this is not really sufficient really to determine the volume of canopies. But currently a second lidar acquisition mission is ongoing. It will finish in 2 years, and now we have about 15 points per square meter on average, and in minimum 5 points per square meter. And this gives us a pretty good idea about the volume of vegetation. And what we are doing now is that we try really in parallel to this lidar acquisition to collect also tree data on the ground, so that we can then use this data for calibrating models based on lidar point clouds. Our objective is that we collect in this time period between 2017 and 2023 about 1,500 reference plots all over Switzerland that are easily accessible and that cover the whole range of potential predictor variables, so variables that might influence the biomass model. So we do this, we have plots in areas with high tree cover and with low tree cover. We have plots in areas with rather high tree height and low tree height of different land use categories, different regions, different altitudes. These are the variables that we considered. And so this is where the plots are located in Switzerland. You see not only settlement areas, it's really for trees outside forests in general. Okay, this is how the plot design looks like. We always have like 10 plots that are really close together, so that field collaborators can collect multiple plots in the same area in one day, and each plot has a radius of 12.6 meters. These are 500 square meters, and there we assess all trees larger than 5 centimeters. We report the tree species, the DBH, the height, the crown diameter. And this is ongoing. We have now more or less half of the area. We have sampled, we have collected the data. And we did last year, we did the first analysis, first evaluation of the data. So we compared we assessed first the biomass of all the trees that have been registered in the field. And then we compared it again with the lidar volume, the green volume that comes from the lidar data. And again, we are very happy that we found this correlation again, this linear correlation. So this is actually the model that we now have first identified. So this is the average height multiplied by the percentage of points that fall on vegetation, so the tree cover, and this is then just the coefficient is 4.374, and this gives us the estimate of the biomass. We had a look whether the different factors that we considered, whether they really have an influence on this model, and we did not find a significant effect. So the relation between green volume and biomass, it was the same for the different regions that we sampled. So for the eastern part of Switzerland and the western part of Switzerland, we did not see a difference. It was the same model for different land use categories that we looked at, for settlement area, for trees and grasslands, and so on. No significant difference here. Also, no difference between the situation in the Jura, so in the northern part of Switzerland, Jura, Mittelland, or in the Alps. Same thing here. And also we did not find a significant effect of the altitude. So the same relationship, whether we are up in the mountains or down in the lowland. And astonishingly, a little bit, we did not even find a significant difference of the tree type. So plots dominated by hardwood or plots dominated by softwood, the relationship between crown volume and biomass actually was the same. Yeah. Okay. So I'm coming to the end. What is the outlook? Where are we going now with this? So we really hope that we have good hope that we can identify some generic models that allow us to quantify the above ground biomass based on lidar data only. And once we have this model, it's in about 2 years when we finish the data collection, then we will be able to do a Swiss-wide quantifying the biomass of trees outside forests, and to produce this wall-to-wall biomass map as we did it for Bern. And the main objective actually is that then we can reassess the biomass stocks of trees outside forests once in future new lidar data becomes available. We can use the same model again to estimate the tree biomass, and then we can also see how this changes over time. We can then really do a monitoring of the tree biomass outside forests without having to go to the field to collect additional data. Yeah. With that, I'm at the end of my presentation, and I'm very open to answer to questions or entering into a discussion, or maybe we do that then also at the end of this morning.
Yeah. And now it's time for questions, and I've seen already that there are 2 questions. So I will thank you very much for this very nice presentation, very interesting presentation to see what's happening in the Swiss context about biomass sequestration and the models that you are creating. So it was really, really interesting. I think many of us have profited from it. So the first question is from Naomi Züricher, and she's asking if there is any concern that in quantifying the biomass, what has not been considered in the condition which informs the functioning of the biomass and greatly impacts on a tree's ability to store and sequester carbon. So if there's any concern in quantifying the biomass.
Not the carbon, the biomass.
Biomass, yeah. In quantifying the biomass, which has not been considered.
Oliver,
yes, maybe.
It's about the condition. The condition of the tree is not considered in this quantification.
The condition of the
correct,
tree.
and condition always impacts all the functions and the result of those functions. Is that a concern?
Yes, that can be. That can be okay. When we sampled actually the trees for and measured the weight for looking what biomass function performs best, we did also not look at the condition of those trees. But yeah, of course, I told you those trees had to be felled for sanitary reasons. So usually these were not the most healthy trees. These were also trees that had some rotten parts in the stems sometimes. So this was somehow taken into account that these are not really the very healthy trees. But of course, this is a variability in the tree biomass that we actually do not assess when we use the models. They do not take into account whether a stem of a tree is hollow or not. So there we have an uncertainty when we estimate the biomass of individual trees. But in general, overall, when we use these functions for measuring trees on a plot or over a whole city, then it is somehow taken into account, because also samples used for this determining those functions, they also had were trees of different conditions as well. So I think it's averaging out. For the individual tree, of course, this is a concern, but when we use the models for hundreds of trees, then it averages out.
Thank you, Oliver. There's another question from Clemens Sirac, and she's asking, do you think that planting and managing trees outside forests as an urban and agricultural area can help reaching the netto null Swiss climate objective of 2050? What is your opinion as a scientist about it?
Yeah, yes, that's a very good question. And of course, trees, they store biomass, the more tree and carbon, and the more trees we have, then when we increase somehow the number of trees, then we increase the sink and we reduce, we reabsorb CO2 from the atmosphere. So this is a contribution, of course, it's not the absolute number of trees that we have at the moment, because usually trees, they grow and they die, and as long as the amount of trees remains stable, also the effect on CO2 budget is more or less neutral. Positively would be when we could really increase the number of trees that we have in our landscape, but I think that we also have to be realistic what is possible and what not. And as I said, the potential is not enormous because we talk more about individual trees. So compared to the possibilities and potential, the sink potential we have in forests, it's rather limited because the biomass density is much lower outside forests than within forests. So even if we would let's say, double the tree areas outside forests, of course, this would be a significant contribution, but still, it would not solve the problem. It could contribute a little bit, but it would not be the solution.
Mm-hmm. Does it answer your question, Clemens?
Yes, thank you, Olivier.
Yeah, I always have to balance a little bit. I think, yes, it is important also to talk about carbon of storage, the carbon pools of trees outside forests, but I think we have also to pay attention that it will not be the silver bullet that solves our climate problem. There we have other, we should maybe put the focus on other elements as well.
There's one last question from Naomi Sterichel as well. Did you include trees growing in the streets of the city in your assessment? The visuals you have shown are only of trees in open.
No, not all trees. When doing this, when selecting these sample areas, we really try to cover all different environments. So park environments as well as built up environments such as streets.
Mm-hmm. Okay, that were the questions that were posted in the chat. Thank you very much once more, Oliver, for this very nice presentation.